Hello. So this is the 2310 exam 2 review. We had issues with our first recording, so we actually have to re-record this. So the formatting of the video might be weird because Varsha and I are not in the same place anymore. So it'll be like 2 videos merged into one, or maybe 2 videos just both published. But yeah, so that's the reason for that. I'm going to go ahead and get us started. This is the list of topics. What I will be covering is all of this and this last one. So in this video, this last one's going to be kind of like moved over to right after this 6, just because I have to do it all in one video. So first we have our XOR and XNOR gates. So first it says to name and draw the truth tables for these 2 gates. This first one here is the XOR, while this next one here is the XNOR. Now how I know this is that N represents the NOT. So this is the one that has this like inverter bubble at the end. It NOTs the output. So that's how I remember that. So we draw the truth tables. I have inputs A, B, and output F. So for an XOR, these are high, or give you a 1 output when both inputs are different. So 1 is a 0, 1 is a 1. So I'm gonna look and I say, oh, so 0, 1 gives me a 1, 1, 0 gives me a 1, and the other ones have the same, so they're gonna give me a 0. For the XNOR, it's high when inputs are the same. And it's important, that I think of it as the same and not just both ones. Because if both are zeros, both inputs are zeros, that is still considered the same. So it'll give me a 1 output. So here I have 0, 0, they're the same, so 1, 1, 1, same, and the other 0. And you notice that these outputs are exactly opposites, and that's because the inverter bubble is put at the end of the gate right here. So it's just the XOR outputs, but all knotted. So then it says, consider the case in which A is set to 0, write equations to express the behavior of f and g as functions of B. So if A is set to 0, let's look at the XOR gate first. If A is set to 0, then we're looking at these 2 lines. Okay, and specifically, what we're looking at is the relationship between B and F. So in that 2 lines for B and F, you'll notice that they're the exact same. So I'm going to say F is equal to B. They're both 0, 1. For G, I'm going to look at those same 2 lines, the B and the G, and I notice they're opposites. They're inverted. So I'm going to say G is equal to B naught. Down here, it says when A is equal to 1, can I color code these? When A is equal to 1, so it'll be the bottom 2 lines of the truth table. I'm going to look at these again. And now F and B are opposites. So we'll say B naught. And over here to the right, I have G, and now they're the same, so B. Moving on, next we have NAND gate conversions and NOR gate conversions. I couldn't really find a good chart for both of these online, so I kind of drew them in. You'll notice that the inverter configuration for this is the same for both. One just has the NAND gate and one has the NOR gate. And I can't give you a good way to memorize this, unfortunately, but I will say if you memorize one, you have technically memorized the other two. Because let's say I only memorized the NAND gate conversions. Well, the inverter of the NOR gate is the same configuration, but with the NOR gate. And then the configuration for the NAND AND gate, this one, is the same as the OR for the other one, just with the different gates. You see how they're the same configuration? And then here, this one is the same as that. So they're like, you just swap the configurations for AND and OR, and then you just change the gates. So as long as you can remember at least one of them, you have the other. And I remember drawing them, I would recommend drawing them down in the beginning of your test on the paper, or at least the beginning of the problem, and then referring back to it. I wouldn't try to keep like trying to remember what the configurations were. Just do it once, draw it, and then refer to it. So then it says draw a circuit that represents the function using just regular AND, ORs, and NOT gates, the two input ones. Draw it as the equation is written. Do not modify the equation. So I'm going to start off. I'm going to see, okay, I have inputs A, B, C, and D. A, we have a NOT, and then that is ORed. I'm going to draw these kind of sloppy, by the way. That is ORed with B. And then we have C and D NOT. So D has the inverter now. And that is ANDed together. And then both of these are ANDed together. So that is what the equation is if we were to just use normal AND, OR, and NOT gates. I'm going to go ahead and copy this for the next parts. And we'll make it small in the corner so we can refer back to it. And I'm going to go ahead and put it for the next part too. Oops. Okay. It says convert this circuit to the NOR equivalents. So I put the NOR gate conversions on the side here for if you're not too sure on them yet, but you do have to memorize this. So don't get comfortable using this. Always derive this kind of all these relationships yourself when practicing. So basically, we're going to replace each of the gates that we drew previously with the NOR conversion that's shown in this chart. Okay, so I start off with A, B, C, D. I look and I see A has an inverter, so I'm going to look in the first row of this table and I see that it should look like this. So this is the, maybe I'll do a bit of color. This is the inverter conversion. I'm gonna cross it out here, so I'm done. I then have an OR gate, so I'm gonna look at the third row of this conversion. And one of the inputs is from A, one of them is from B. So this is all OR gate. Moving on, the D also has an inverter. And whenever you draw these, you don't have to write these like inverter or like these circles and stuff. I'm just doing this to show you how I converted these. On a test, you won't have to write all that, but it might help you. So it might help you be organized about it. And then we have an AND gate. So that is our AND gate. And then both of these are ANDed together. So that is our AND gate. And now we are done. What comes out is F. I'm gonna move this slightly. So now we're not done yet. We do have to simplify more. So what we have to do is we have to get rid of double inverters. So we're gonna look for when two of these are right after each other. Why? Because whenever we have double inversion on something, an input, they cancel out. Because you invert it, you make it, so if it was a 0, you invert it, you make it a 1. You invert it again, you make it back to a 0. Nothing really changed, right? So I'm going to look through, and I'm going to try to find where I see double. So I see one right here. Those two are inverters right after each other. I see one down here. Those two are inverters right after each other. And actually, those are the only two places that I see this happen. So now that we have canceled, I'm going to redraw this circuit without those. So I have A, B, C, D. And I'm just redrawing them without the gates that I got rid of. Sorry that I'm drawing it very messy, but just want to get this all done. And that's the final, this is the final circuit. So now let's do the same thing, but instead of NOR, we now have NAND. Same process, everything just different conversions. So once again, I'm going to look, I'm gonna be like, okay, I have inputs A, B, C, and D. A has the inversion. So this is the inverter. And then we have an OR. That was kind of ugly. We have an OR gate. I should label that as my OR gate. So this is my OR gate. Down here, I have another inverter. And then now an AND gate. So this is my AND gate. And then those come together for another AND gate. I'm running out of space, so I'm gonna move this over a bit. So then this is our other AND gate. Okay, same thing, we're gonna go look for double inversions. So I see one right here, and then I'm looking, and that's actually the only one I see. So this one doesn't cancel out as much, and sometimes you'll have those cases, especially when you do both NAND and NOR. Usually only one of them simplifies quite a bit compared to the other, which is why we recommend why we're making you do both for the same circuit, because it kind of shows you how sometimes one is better, the NAND is better, for example, and sometimes the NOR is better. Yes. So I'm going to make this smaller and in the corner, and then we're going to redraw this. Oops. So this is the circuit I end up getting as my final answer. Still looks pretty complicated, but there's just nothing else we can simplify. Moving on, we have muxes, encoders, and decoders. So for a mux, it always has multiple inputs and only one output. That's important. If it has, sorry, let me write this down. If it has more than one output, then you're probably looking at an encoder instead. So a mux, what it does is the select lines will give you some binary number, some 2-bit binary number, right? And I show it in this chart here. Now, depending on what that binary number is, one of these input lines will be selected to push their data through as the output. So let's say, for example, we have 0, 1 as our select lines. That is the same thing as 1 in decimal. So this I1 is going to basically be connected and come through as the output. So y will be equal to I1. If we were to change that, now we say 1, 1 instead. Now I3, because 1, 1 is 3. So now I3 is going to go through, and y will be equal to I3. Moving on to encoders. Encoders have multiple inputs and less outputs. Basically, encoders, and I show it on this chart to the right, the inputs are 1 hot. Only 1 bit is on at a time. And based off what that 1 hot is, they'll change it to binary. So like, let's say D3 was 1 and everything else was 0. Then D3 is going to put 3 in binary as the output. So it's going to put 1, 1. Okay, well, let's say D1 was on and the rest were off. Then, sorry, D0 was on and the rest were off. My bad. Then Q0 and Q1 would be 0. And we can see that in this first line of the chart. So basically, we just have one of the inputs on, then its corresponding binary number will come out. Decoders are kind of the opposite. They have less inputs than outputs, and their inputs are now binary, and their outputs are 1 hot. So the inputs, the decimal equivalent, whatever that output is going to turn on. So if I have 1, 0, that is the same thing as 2 in decimal. So Q2 is going to turn on and all the rest is going to turn off. Now let's say I had 0, 1. So 1 in decimal. Then Q1 is going to turn on and all the rest are going to be off. So that's kind of the process that you go through with these. The questions that you'll be doing with decoders are more memory-based questions. So it says, what size decoder is required to address a 512 by 16 RAM memory bank? So essentially we have a RAM and it's connected to a decoder. And this decoder will basically tell this RAM what address to store data in. Okay, so when we have a 512 by 16 RAM, and we're talking about the decoder, all we really got to worry about is this 512 portion. Basically what this is saying is that this RAM has 512 inputs, which means that's actually the outputs from the decoder, as I showed above, because we connected them. So that means that the decoder has n by 512, where n is the number of inputs. And the relationship between outputs and inputs is that the number of outputs is equal to 2n. So in this case, we have 512 is equal to 2n. So you can just plug this into a calculator, try to find what it is, but you should get that n is equal to 9 for this to be true. So this means we are working with a 9 by 512 decoder. 9 is the number of inputs, 5 is the outputs. It says how many address lines or bits are required. We actually just solved for this. There are 9 address lines because, like I said, the way they're connected, the address lines will go into the decoder so that the decoder will essentially pick the right line in the RAM, the right place to store the data. But the decoder is what gets the address first and then tells the RAM what to do. So the address lines are the inputs to the decoders. Next, it says what decoder input is required to access row 165. This is just a, oh, I'm so sorry, might be noise here. This is just a simple binary conversion. But what's important is we need to know how many bits. It's important to realize, oh, we're doing a decoder input, which means we have to have a bit for every input line of the decoder. We said that the decoder has 9 inputs. So that means our answer has to have 9 bits as well. Okay. Our answer has to have 9 bits as well. So whenever we convert this row 165, we just got to make sure that we add any leading zeros at the end to make it 9 bits. So I'm going to convert 165. I'm going to use the division method, use whatever method you want. 82, remainder 1, 41, remainder 0, 20, remainder 1, 10, remainder 0, and 5, remainder 0, 2, remainder 1, and then we're going to kind of have to go over here. 1, remainder 0, and 0, remainder 1. So if I read those from bottom to top, remember bottom's all the way over here, I have 1, 0, 1, 0, 0, 1, 0, 1. So now, like I said, we have to make sure this is 9 bits. So I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 bits. So I need to have 1 right in front. A 0 right in front to get those 9 bits. And that is my decoder input. If you don't put enough bits that's required, or if you put too many, then that's probably wrong. You need to make sure you have the correct number, which is easy because we solved for it before. You just have to remember. The next one is the same thing. So I'm going to move on. We're just going to skip that. So next we have our adder-subtractors. For this one, we're going to work with adding. We're going to do 5 plus 2. What's important to note is that we have these XOR gates. And what does an XOR gate do, essentially? You could just draw their truth table, if you remember that more. Just draw it up here. But what I remember is that XOR gates give me a 1 if inputs are different. If inputs are different, it gives me a 1. Okay, and it's important to know this XOR gate relationship. So we have an add subtract control. You're going to put a 0 if it's adding, or a 1 if it's subtracting, and you'll kind of see why that is whenever we work through all of this and how it works out in our favor. So I'm doing 5 plus 2. A is 5, B is 2. So I'm going to do the A inputs first. 4-bit binary, just converting 5 to 4-bit binary. So we have 0, 1, 0, 1. Maybe I'll use a thicker line so you can see better because there's so many lines. So 0, 1, 0, 1. And then for B, we have 2. So it's going to be 0, 0, 1, 0. Okay. And then I'm going to go ahead and shift all the A numbers down just to make them easier to see later. And I'm also going to bring that add subtract control all the way to this very right carry in where it's connected to, just so whenever I look at it, I don't have to go all the way back and look at it over here. So now we have this XOR gate that we have to deal with. So I'm looking at the B3 XOR gate, this one first. You could start with any one, but I'm just looking at that one. And I'm looking, I say, okay, we have a 0 from B3 and we have a 0 from the add subtract control line. 0 and 0 are the same, they're different inputs, so what comes out is going to be a 0. Next one, 0, 0 again, so 0. Next one is 0, 1. The inputs are different, so what's going to come out is a 1. And then next is 0, 0, so 0. Now, whenever you do these add subtract controls, you're going to have to start on this right adder. And that's simply just because like the way the carry in is on the right side. So you'll notice if we follow these carries and the carry outs, they go from right to left. So we start with this very right adder. And we have a 1, a 0, and a 0. So 1 plus 0 plus 0 is 1 with a carry of 0. 0 plus 1 plus 0 is 1 with a carry of 0. 1 plus 0, 0 is 1 with a carry of 0. And then 0 plus 0 plus 0 is just 0 with a carry of 0. So we look at this and we see 5 plus 2 is equal to 7. So as our answer, we should be getting 7, which is what we get if you convert this to decimal. Now we have this add subtract control, 5 minus 2 is what we're going to do. So A and B. So our A and B inputs are actually the same. So I'm going to go ahead and write the A inputs, 0, 1, 0, 0, 1. That's 5. And then 2 is 0, 0, 1, 0. This add subtract control, I'm now going to put a 1 because that's what we do for subtraction. And you'll see how that changes things up. And I'm going to go ahead and write that over here as well. I'm going to shift down the A value. So I have 0, 1, 0, 1. And now we have these XOR gates. So this first B3 XOR gate is the one I'm looking at. And I see it's connected to both a 1 and a 0. Those inputs are different. So we have a 1 output. Next one, once again, 1 and 0. So 1 output. Next one, 1 and 1. So they're the same. So I have a 0. And then next, I have 1 and 0 different. So that's a 1. Now, starting from this right full adder, I have a 1 plus 1 plus 1. So one of those is going to be the output, and then the other two are going to be that carry. We have 0, 0, 1. So 1 output, 0 carry, 1 plus 1 plus 0. We have 0 output, and 1 is carry, and then 0 plus 1 plus 1, which is 0 with a carry of 1. Remember that in subtraction, we ignore the carry out. So whenever we check our answer, I'm only going to look at these. And when I convert that, I get 3. Positive 3. Remember, this is positive because there's zeros in front. But yeah, so I get 3, which is what should be. So we're good with that. Moving on, we have comparators. I don't know. We have comparators. So it says our A input should be equal to 3 and our B input should be equal to 6. So I'm going to write that down into 4-bit binary A3. So I have 0, 0, 1, 1. That's 3 in decimal. And then for B6 is 0, 1, 1, 0. Maybe I should just stick to the thicker line. Okay. So going ahead and moving that into each of the digits, the comparator, A3 we got was 0, and then A2, 0, 1, 1. B inputs were 0, 1, 1, 0. So this is the starting point. It moves from left to right. But what's important to note is that we have to figure out what we're going to set these greater than, less than, and equal to. There's only one answer in this case. We have to set it to equals. If you set it to greater than or less than, like let's say you set it to less than instead, it's not even going to look at all the digits and it's just going to put a 1 in the less than all the way through. And we don't want that. We want it to look at the digits and compare them. So we have to set it to equals. And there's a reason that we do this. You might be thinking, well, what if later on the number that we thought was smaller at first gets enough ones that it overtakes the other number? I'm going to tell you now that that is impossible. So let's take a scenario real quick of binary 8 and then. So if we were to have a comparator, we would compare this first digit and we would say, let's say this is A and this is B. We would say, oh, A is greater than B. And from there, I would know that A, it will always be greater than B in this case. But you might be unsure. Why is this the case? What B has so many ones after and A has so many zeros, so what if B gets more? If we convert these two numbers to decimal, we get 8 and 7. Because just the way that we organize binary is if we want any more than all ones, we have to add another digit. We have to add another bit. So everything after that initial bit is less than it, because we needed to add the extra bit to represent that bigger number to begin with. So it's actually impossible, no matter how many ones and zeros I put after these cases, it's impossible for B to suddenly grow larger than A. I hope that made sense. So I'll leave that up there. So that's why it's important to set it equal, because this comparator goes off of that kind of rule. So if you tell it less than and greater than, it won't even look at the next ones. It's just going to keep going. So we have equals then. We look at this first digit, we see, oh, A is equal to B, so it's going to stay equals then. We look at this next one, and now we finally have a change. A is less than B. And it's important you keep it in this A, B, and you don't suddenly change it to B is greater than A. Because in this case, A less than B would say less than. But if you were to suddenly change it, you might think, oh, it's actually greater than. But we're talking in terms of A first, then B. So this is less than. And now that it is less than, we don't even have to look at anything else. We can just put this all the way through. And we have less than all the way. So even though this one right here, this digit 1, has them equal, we don't suddenly change it to equal. Because like I said, if it starts off, once you find that it's less than or greater than, that's it. You're done. It goes all the way through. Moving on, we have timing diagrams for single flip-flops. So this is a flip-flop without an enable and reset. So the important thing to know about flip-flops is that rising edge is the only place where you store data. Not the falling edge, not in the middle when the data changes, only that rising edge of the clock. So I'm going to draw a line on every rising edge of the clock just to make sure that I don't miss one or I don't accidentally change on the falling edge or something like that. This beginning portion, I have to draw a line in the middle because we don't know what goes on there. We haven't hit our first clock. We don't know what was stored there. I mean, we can kind of see it here, but what I mean is, if, let's say we had a flip-flop and we hadn't turned it on in 5 days. Well, whenever we turn it on, we don't know what was stored last. That was 5 days ago. Maybe we have some records, but we just don't know, you know? We don't know what's stored in there, what it initially starts off with. So until that first clock, we are unsure, and we have to put that question mark there. Okay? When first clock, the rising edge comes, we store the value in D. So D at that moment is a 0. You'll notice I drew it to change a little bit after the rising clock. You always want to draw with a slight delay. Because in the real world, whenever we have all these complex circuits, there's always a delay. It never exactly changes on the clock. So we have to account for that, because if you don't account for delays, you run into issues. So we draw it that it changes a little bit after the clock. And I would recommend that whenever you draw these lines, just draw it past the clock a little bit every time. So then here, we look at what D is. D is still a 0, so I'm going to draw it, and I'm going to draw a little bit past the clock. Here, D is 1, going up, a little bit past the clock. Still 1. Back to 0. Back to 1. Back to 0, and then back to 1. So that is my signal timing diagram. Now, let's do this for an enable and reset. Essentially, enable tells us, oh, you can take data. It gives us the flexibility to decide when we want to take data. So we don't take data every single clock. We can say, actually, hold the data you currently have. Don't get new data yet. So it gives us more control. Reset makes it so that whenever it's high, we reset the data to 0. Because before we said we don't know what the data is, so we're kind of just resetting it to a known value, which is 0. There is a hierarchy to this. You want to always look at reset first and then enable before you do your clock and input. Reset takes higher priority over everything else. So yeah, we are still doing rising edge. Okay, flip-flops only take data on the rising edge. So I am drawing all our rising edges again. And in this initial part, and this is important, we still are in the unknown state. We don't know what that is. And you don't have to draw like a question mark every time, but we're still in that middle. And you might be wondering, you might be like, but you said if reset is high, then we have a 0, and reset's high right here. But remember that I said that you do not change values until the first clock has happened. A flip-flop does not store values until the first rising edge of a clock. Every rising edge of a clock. So even though that reset's high, we haven't reached the clock yet. So we can't take in data yet. We can't change our values. So now I'm going to have to draw a little bit past. Still do delays. Don't forget about your delays. I'll write it up here. Reminder, delays. We reached the first clock, and at the first clock, we see that reset is high. So automatically, we just say, oh, 0. And what I notice is that reset is 0 everywhere else. Reset only was a 1 in the beginning. So we actually don't have to worry about it anymore. But it's possible to throw in a trick where all of a sudden reset's high in the middle. Is it practical? No, probably won't happen. But good. So always be careful. But I noticed that reset's 0 after that, so I'm going to ignore it. So now I only have to worry about the enable. At this clock, enable is high, which means we can take D in, the input, and D is 0. So we're going to hold 0 till the next clock. Here, enable's high, D is 1 now, so we can move up to a 1. Here, the enable is low. You see that? It's low. It's 0. So we have to hold this value. We can't change it. No matter what D is, we don't change it. Here, enable is still low. So we have to hold this low again. Oops. So we have to hold this low, hold, and then here enable is finally high again. We look at D. D is coincidentally 1, so we have that same value go through. Okay. Now we have the 4-bit registers. So 4 bits, we can represent numbers 0 through 15 in binary. These are essentially your hex numbers. So once you get to like that 10, 11, whatever range, you start going to that A, B. So that's just why we have letters and stuff here. This is the same thing as our single flip-flop without enable and reset. Where at each rising edge of the clock, we will just store whatever data is there. So for these, you still have to draw with a delay. So I'm actually going to draw my boxes now. You still have to draw with a delay. So I'm just going to make it so every box kind of starts a little bit after the clock, the rising edge of the clock. This beginning part, we don't know what's in that, remember? So we have to denote it with a question mark. We do not know until the first clock where it takes in data. Next, that clock has a B, so we'll take that in. Then, sorry, it's kind of thick and hard to read. We have a B, and then we have an 8. A 4 is at that clock, D, C, 0, 3, and E. Moving on, I'm going to draw my rising edges again. Once again, going to draw my boxes a little bit after the delay, or sorry, a little bit after the clock because of the delay. But now we have a reset and load. So reset's the same as before, where it kind of takes precedence, or it's the first one you look at. Load is just another word for enable. So it's going to work the same way. It tells us whether we want to load data in, whether we will look at the input and change our data accordingly. Okay, so this beginning part, remember, we don't know what's in it. And then we look at this next clock and we see reset is high, so automatically a 0. And I will recognize from here on out that reset is low, so we do not have to worry about it anymore. We only have to worry about our load. So then this next clock, I'm looking, load is high, so we can take from A the input, which is 8. Load is still high, so 4. And then here, load is low, which means we just hold that 4. We don't look at the input. Next, load is high again. We check. Oh, it's a C now. Next one, load is high. We have a 0. And then next one, load is low. So we're going to hold that 0. And then load is high. So we're going to take that E. Moving on, we have, this one looks more complicated, but it's essentially the same thing. So the outputs B and C share the same input, which is A, clock, and reset. The only thing they differ in is their loads. We have 2 loads. By looking at this diagram, I see that L1 corresponds with B, so I'll write it here to kind of show you, and L2 corresponds with C. So those are the loads for those separate outputs. And it's just so we can have 2 different memory spaces, and we can tell one to start storing data at a certain point, with the other one to like hold an old data and then swap it. Like, it gives us more flexibility. We have more memory that we can kind of choose when to take data. So once again, we do the rising edge. Once again, whenever we do these, reset's always first, and then the loads are second. Yes. So we're still in the 4-bit, so I'm just gonna go ahead and draw the boxes for both. Get that out of the way. These are very messy boxes, but you understand. And then we'll just do one at a time. So I'm gonna look at B first. I'm gonna say, okay, reset is high, automatic. Oh, I almost messed up. Beginning, what is it? Remember, it's always unknown. We don't know. First clock hasn't happened yet. Now, first clock, we see reset is high, so it's gonna be a 0. The next clock, I also noticed resets low from then on, so I'm not even gonna look at it anymore. This next clock, load 1, the load for B is low, so we actually hold this 0. Next one, load 1 is still low, gonna hold that 0. Next, load 1 is finally high, so we're gonna take that D from A. Next one, load is low again, so we're gonna take that D. We're gonna keep the D. And then next, load is high, so we're gonna take that 0. Next, load is high, so we're gonna take that 3. And then load goes back to 0, so we're gonna keep that 3. We're gonna hold that 3. For C, we're now looking at load 2 instead. First clock, reset is high. We don't look at anything else. We just put a 0. Second clock, reset is now 0 from then on, so I'm going to ignore it. We have load 2 is high, which means we take that 8. We have that load 2 is still high, so we take that 4. Load 2 is still high, so we get that D. Load 2 is still high, we get that C. Load 2 is now finally low, it's 0, so we have to hold that C. And then load 2 is high again, so we get that 3. And then load 2 goes back to low, so we have to hold that 3. So same process, it's just now we have a little bit more to take care of. So this next part is all going to be done by Varsha. I'm going to skip all the way to the end where I have this. So you'll have to know gray code, binary encoding, and one-hot encoding. Gray code essentially is just changing only one bit at a time. So you kind of rearrange orders a bit. Think of your K-maps. Whenever we draw a K-map, and we have like A, B, C, D, we do 0, 0, 0, 1, 1, 0, 1, 1, right? But that's not really in binary order. So binary encoding, you would say 0, 0, 0, 1, 1, 0, 1, 1. But in this gray code, we instead do 0, 0, 0, 1. Oops, I wrote my K-map wrong. My bad. It should be 0, 0, 0, 1, 1, 1, 1, 0. My bad. So then here it would go 1, 1, 1, 0. So this is just regular binary counting. It's 1, 2, 3, 0, 1, 2, 3. My bad. And then this is the gray code because we only wanted one bit to change, so we kind of rearranged these these 2 lines right here. We kind of swapped them to make it so only one bit changes. So actually what we have here is 0, 1, 3, 2. And you might be like, well, why do we do this? That's kind of weird. What is the point? It's just a troubleshooting thing. So if you were to do a physical circuit with gray code, then the computer would be like, oh God, more than one bit changed at a time, we probably have an issue here. So it's mainly just a troubleshooting thing, which may be why you're thinking, oh my god, that's so weird, why would we do that? But yeah, so that's gray code and binary encoding. Binary encoding is just counting up in binary. Like I said, one hot encoding is when only one bit is one at a time. So that's like whenever we were looking at the decoders and encoders, and you had like 0, 0, 0, 1, 0, 0. And it seems just like that one is just kind of moving along the 4-bit binary number. Okay. So this one tells you to alphabetize, then do binary encoding, then gray encoding, and then one hot. So I'm sure you all know your ABCs, so I'm just going to kind of write these fast. We have basketball, football, hockey, ping pong, soccer, tennis, track and field, and volleyball. And I'm gonna kind of make like rows, just so whenever I write these binary numbers later, it's easy to see which ones correspond with which. Oops, that one kind of cuts through. That's fine. There we go. So that's the ABCs. Next, we encode into binary. Oops. Just gonna rewrite that. So for binary, we simply just count up in binary. But now we come across the question of how do you know how many bits to use? So in this case, I counted them for you. We have 8 total sports. Which means in binary, we can represent this as 0 to 7. Because remember, binary, you start counting at 0. 0 to 7, how many bits do you need to represent that in binary? 7, you only need 3 bits. The largest number, you only need 3 bits. So we're going to write our binary in 3 bits. So we start off with 0, 1, 2, 3, 4, 5, 6, and 7. Okay. Moving on, we're going to go to gray code. So gray code, remember I said, is you only have 1 bit changing at a time. It actually uses the same number of bits as binary because we're kind of just reorganizing the binary numbers. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0. Oh, sorry, not 0, 1, 0. That's not changing 1 bit, that's changing 2. So then we have 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, and 1, 0, 0. Now, when you do this part, you might get something different, and that is okay. Because we have so many binary numbers, we can actually represent this gray code in different ways. So for example, after this one, so we have 0, 1, 1, we could have changed it to 1, 1, 1. And then we could have been like, oh, 1, 1, 0. And then, 1, 0, 0. You know, we could have gone a different route. And then like 1, 0, 1. I might be missing something. So 0, 1, 0. Anyways, what I'm saying is there's multiple ways to go about this. And if you find another one that works, then good. you'll still have a correct answer. Okay. All you have to make sure is that you don't have a repeat and that you don't suddenly change 2 bits instead of just 1. You have to change 1 bit, but there are multiple answers. You might get a different order, and that is okay. So then we have 1 hot. 1 hot, like I said, is just each one will only have 1 bit as a 1. So for this, you will need more bits. You will actually need 8 bits. You will need the same number of bits as many items that you're representing, because you can think of it as each bit represents each of those items. So like if I have 1, 2, 3, 4, 5, 6, 7, 8, in this case, this 1 all over here, I'm going to say represents basketball. So I have that as a 1 and everything else is a 0. And then if I keep going, I kind of shift that 1 over. Well, this second bit I'm going to say represents football. So now basketball is at a 0. You see how I use I have to have 8 bits, a bit for every single different thing I'm organizing, so that each one has its own place almost that we will put as a 1 once it's their turn. And then we'll keep going, just shifting that 1 over. Did I miss 1 somewhere? 3, 4, 5, 6, 7. Oh yeah, I accidentally have been writing 7 bits instead of 8 just now. Let me fix that real quick. So I have 1, 2, 3, 4, 5, 6, 7, 8. There we go. 1, 2, 3, 4. So you should have that you end up with the 1 all the way to the left. If you still have a 0 in front, you might have used too many bits, or maybe you messed up somewhere. But that is how you do binary encoding, gray encoding, and then 1 hot encoding. And that is the end of my portion.
Hello, everyone. Welcome to the CEE 2310 exam review, part 2. These are the topics that we will be reviewing. Part 1 covered all of these topics. I'll be going over topics 6 through 12, which is memory architecture, binary arithmetic, and IEEE floating point representation. So let's get started. These first couple of slides are going to review register files, memory, and some of the specifics of each before we go into an example. The important things to note is that when you have, register files and memory, both are for storing data. Memory is typically for longer term data. Register files are for immediate use. So let's say we have a program that we're putting into the computer. We're going to have, in a program, we have typically data and instructions. A register file stores these instructions while it's during use. Memory typically stores data and instructions for the whole program so that it can have access to them as the program is running. So because a register file only stores instructions that are currently in use, they're typically small and high-speed storage directly in the CPU, or very close. They only store the ones that they're currently processing, so they can quickly access and manipulate the stored data. The storage capacity is typically represented in bits. So if you have something called a register file has 8 bit registers, that means you have 8 flip-flops that are storing each of the one. So that means you have 8 flip-flops, each storing 1 bit of data. Memory, in contrast to register files, is typically larger and more long-term storage. You can have short-term memory, which is what you'll see with SRAM and DRAM, but they are much longer storage. They're much longer term storage than register files. Memory is typically of two types, primary and secondary. Primary storage is internal memory, so that is your read-only memory and random access memory. And then secondary types of storage are like those that are kind of external to your device, typically hard disks, CDs, DVDs, and so on. Storage capacity for memory is expressed in bytes because you have so much of it. So you can have it as gigabytes or terabytes. So moving on to random access memory. This is a type of primary memory. It is volatile, meaning that when you cut power to the device, all your data is lost. Because it's volatile, it is temporary storage of all the programs and the data that are being used by the CPU. The key point in random access memory is that you can read, write, and erase as many times as you want. Data is always stored in gigabytes. It's smaller when compared to read-only memory. So that's why they've got gigabytes of data here versus like terabytes or megabytes of data in read-only memory. The two types of random access memory that you have are static RAM and dynamic RAM, or SRAM and DRAM. Let me write that. SRAM and DRAM. We'll go through the specifics of how each of the DRAM and SRAM cells are organized, but in general, SRAM is made of 6 transistors, while DRAM is made of a transistor capacitor pair. This is the block symbol for a RAM. If you notice, there's a read and write and an enable, which lets the memory block know that you're reading and writing. In contrast, read-only memory is non-volatile, meaning if you have data that you're storing, even if you remove power to the source, data is still retained. It's long-term storage of data that's typically pre-recorded, like firmware, your microcontroller code, or BIOS code on your computer. Data is only read, meaning that you can't program it yourself. It's typically been programmed beforehand and then handed off to you. Access is typically slower than the RAM because read-only memory is stored a little bit further away, or also it could also be just like an external device. And then data is retained even when power is lost, as we've discussed. The couple of different types of read-only memory are PROM, EEPROM, and mask ROM. We'll see some more examples of read-only memory below. And then if you'll notice here, when in the block symbol, you only have an enable and not a read-write enable as well, which means, as the name suggests, you can only read from memory. This is some of the important information to know when you're comparing register files to these types of RAM and ROM. The cost of a register file is very high because register files are composed almost exclusively of transistors. And because of their proximity to the CPU, as in they're very close and they're directly on the same chip, access speed is extremely fast. SRAM is a little bit less expensive when compared to register files, but more expensive than DRAM because again you have 6 transistors, in an SRAM, and the access is pretty close. Register files is about 1 to 10 nanoseconds, and close proximity wise, it's relatively close. DRAM is much more cost effective compared to SRAMs and register files, but access is a bit slower and it's positioned a little bit further away from the CPU, meaning that it's off the chip. And then finally, read-only memory is the cheapest form of memory storage compared to all of these other ones. It has the slowest access speed just because the ROM can be stored either on chip or off chip. And then the CPU has to go and get these instructions from like a relatively far place. Just note that when we say that it's fast or slow, that we're only talking about the difference of nanoseconds. When it comes to like clock cycles, nanoseconds do matter a lot, but for our purposes, they're all pretty fast in terms of speed, just like as relative to like seconds of access. So this is what a register file looks like. We discussed that register files are composed of registers. You have multiple registers in a single file. And the way you denote the size of a register file is when you say n by m, where n is the number of registers and m is the number of bits per register. So look over here where we have an example of a 4 by 8 register file. That means we have 4 registers, and each register stores 8 bits of data. And as you said before, that each bit is 1 flip-flop. So that means each register here has 8 flip-flops in it. Decoders are typically used to select which register to read or write from. Usually you only have one write register here, and then you have multiple reads. So it's not shown. You can have another read block, or as many as you need in order to read the data from these registers here. This symbol here notes that it's a clock. You should remember that from flip-flops as well. And this is the symbol for a decoder, which Megan has gone over in part 1. A RAM memory block is a little different from the way register files are represented. Typically, you write it as words and bits per word. So the words just mean the number of address lines that you have here, and bits per word is just how many SRAM cells do you have in a row to store the data. So in this example of the SRAM cell, what you have is a 4096 by 64, which means you have 4096 address lines or words. Address lines, words. And then each word has 64 bits. That means you can store 64 bits of data that each go into one of these SRAM cells. The structure of an SRAM cell is like this, where you have a transistor, and then a sort of like a little network of NOT gates, and then another transistor. Remember that NOT gates are made of 2 transistors. I'm going to write 2T, 2T, and then 1T. So when you count up the total number of transistors in an SRAM cell, you actually will have 6. The NOT gates are just used for more concise representation of an SRAM cell. A DRAM cell is made of a transistor and capacitor pair. The transistor can either be an NMOS or a PMOS type transistor. And it's because they have just one transistor in a DRAM cell that DRAM cells are cheaper to manufacture than SRAM cells. And you can actually pack more DRAM cells together just because of their relative size. Okay, moving forward. This is a ROM memory block that is composed of just different ROM cells. The structure of a RAM and ROM is pretty similar, so you're going to use the same notation to describe it, where you have words and bits per word. And decoders are still used to select the address lines to write data to the correct row of cells. So if I have data coming in from here, I use my decoder to decide which of these rows I want to send the data to in order to store them. These diagrams down here represent the different structures of mask ROM, OTP ROM, EPROM, and EEPROM. We'll see a couple of examples of those in a little bit. But each of these blocks are cells. Actually, let me write that. This is a ROM cell. And then I put a star over here just to note that before in the SRAM cell, we had a read and write enable, but here we only have one enable, because we're only allowing it to read. Okay, so a couple of exercises. Megan's gone over these first 2 questions in part 1. So I'm going to have you guys look at the video, part 1 video, in order to get answers for that. We're going to go directly to 8C, where it gives you an SRAM cell and asks if the word enable needs to be high or low to read or write from the cell. The key things to note that this is a PMOS. I know in the diagrams above that we've seen these as NMOS transistors, but here in this particular diagram, it's a PMOS. So let's remember, for a PMOS, in order for it to be active, you need to send a low signal, right? So enable has to be 0 or low in order for this PMOS to be active, and close the switch in order for data to pass through. So that is your answer. For the DRAM cell shown on the right, the word enable needs to be high or low to read or write from the cell. So if we look at it again, this is an example of an NMOS transistor, and enable needs to be high in order to activate that NMOS. For part E, when reading from left to right, it's asking you which binary number is programmed into the ROM cells shown. ROM is a little bit, sorry, this particular one is a little bit easier to understand just because whatever you have on these data lines here is what you're going to have as your output. So let's write 1100. So that's the binary number that's being programmed into this these ROM cells. And then for OTP ROM cells, remember that OTP ROM is an example of memory that is permanently programmed. So they typically have fuses like these, which you blow up or destroy in order to store a 0 into that particular cell. So I'm going to write X means that you're storing a 0. So if you're storing 0xa, which in binary is 1010, which is like decimal equivalent 10. Decimal equivalent is 10. So if I want to store 1010 into these cells, what I'm going to do is blow up these cells here. That's 1010, and that is how I store a hex value of 0xa into this this memory block, memory cells. The most common questions that you'll see on your exam are identifying the type of memory given a scenario. These definitions here, I've highlighted a couple of words that I like to look for when I'm walking through each example, but I'm going to actually walk you through the flowchart on the side. So the key to identifying the type of memory is first deciding whether you have a volatile type memory or a non-volatile. Remember that volatile means that when you lose power, all your data is lost, and non-volatile is when you lose power, your data is retained. So suppose we have a volatile type memory, then you have to decide whether it's RAM or a register file. Register files are used for very small amounts of data, and in which two or more independent entities can access at the same time. Typically, in the scenarios where you'll be using a register file is something where you have sensors involved. So there's that. If you have RAM, you're looking at something that needs to be stored a little bit more longer term. So things that you need to work on, let's say for like 10 seconds or 30 seconds at a time. So the way you decide whether you have SRAM or DRAM is SRAM is for small amounts of data, DRAM is for slightly larger amounts of data. So then in the case you have a non-volatile type of memory, you have to decide whether it's non-programmable or if it's programmable. In the case of a non-programmable memory, you either have mask or OTP ROM. Remember that mask is for mass producing, or mass-produced products. So they'll have the same data stored for like thousands, tens of thousands of products, and so on. The key when you have OTP ROM is usually when the scenario tells you that it's a unique code, or if it's programmed for a very few, like even if it's not unique, if you've only got like 10 devices or 12 devices that you're coding, then it's an example of OTP ROM. So finally, in terms of programmable memory, this EPROM is either 1980s technology or it requires complete removal from the circuit to be reprogrammed. EEPROM and versus flash, the way you decide which one's which is in the case of flash memory, you have a very large amount of data that needs to be erased at the same time and reprogrammed. Whereas EEPROM, usually you erase bytes at a time, just like small pieces of data, in order for you to reprogram it. So let's check out some examples. So in this first scenario, your vehicle audio unit contains a memory with a unique security code. So as we've discussed, unique security code usually means it's OTP ROM. In our second scenario, we have a digital photo frame that can be changed at any time. So we're looking for reprogramming. And it's displaying a photo every minute. So if we look at our little flowchart, we know that it is programmable, which means it's a non-volatile type memory. It can't be EEPROM or EPROM just because you want to be able to change large amounts of data at a time. So that leaves us with flash. In that scenario, the car can be programmed to select the driver's favorite stations, but the programming is lost if the car battery dies, which means that we have an example of volatile memory. We know that it's being programmed, and so the favorite radio stations are a bit of a larger type data, and you want to access it after you've programmed it. So it's either between SRAM or DRAM. It can't be DRAM because that's too large of memory that we need. So that leaves us here with SRAM. In this fourth scenario, we have popular, meaning mass-produced. It has 3 pre-recorded messages. So the only type of memory that we have that is mass-produced is mask-programmed ROM. I'm just going to be writing mask over here. So a video gamer is relying on this type of memory to maintain the current picture while they're playing. So current picture while they're playing. So a current picture is something that it'll update regularly, like within like seconds, milliseconds, and so on. So it's a type of volatile memory. It can't be register files because that's for very small amounts of data. It can't be RAM for the same reasons, which leaves us with DRAM. A portable device is storing members of active club members. So we know that it's portable. They're individually added or removed. So we know that it is programmable type of memory because you're adding or changing names. It can't be EEPROM because that requires a whole circuit to be removed. It can't be flash because that is too large of a data type. So that leaves us with EEPROM. In this other scenario, the keyword that you're only looking for is that it's 1980s type memory. So let's write EEPROM. And in this last scenario, it could be process of elimination, or you can remember that sensors typically mean that you have a register file to store the data because you are kind of you're writing all of these parameters while at the same time reading them. So that you're not really storing large amounts of data. So I'm just going to write RF to represent register file. Okay, in these next set of questions, the first thing that it tells you that it's BIOS, the basic input or output system code. It's a large amount of code, and the fact that you can remove the chip for it's hard to remove the chip, but you can remove if it needs to be reprogrammed. So the only type of memory that fits the bill is that it needs to be non-volatile because you don't want your computer to lose all its code when you turn it off. It's programmable, and it can't be EEPROM because or flash because those are relatively easy to reprogram. So it leaves us with EEPROM. In our next question here, we have a unique ID number being the keyword. So I'm just going to write that as OTP-ROM. In this next scenario, we have that it's mass-produced, which means that it is mask-programmed ROM. A digital radio is continuously recording for the last hour, so we've got a large amount of data from the time that the radio is turned on, and we know that the recording is not saved when the radio is turned off, which means we have a volatile type memory, and it's going to be DRAM. The register files in SRAM are too small, which leaves us with DRAM. A farmer has deployed microcontrollers to monitor moisture conditions in his fields. You have sensors, which indicate to us immediately that you have a register file. In this next scenario, you have a microcontroller that uses small memories to store variables at runtime. They are not needed after the run has ended, which tells us that it is a volatile type of memory. It can't be a register file because you need those variables throughout runtime, so it's a type of RAM. You don't need DRAM because it just says small memory, which leaves us with SRAM. In our next question, we have a microcontroller's largest memory to use sketches or programs. The program can change at any time, and it must remember the latest version when power is turned off. So that tells us it is non-volatile, it is programmable, and because you're storing entire programs, it is a large amount of memory, which means that we're using flash memory to store it. And for our last scenario on this question, you have a portable device, easily added or removed using buttons on the device. Items are a very small amount of data here, so we know that it is non-volatile, it is programmable, and small data means that it's EEPROM. Okay, moving forward to our last set of questions before we move on to another topic. In this first scenario, it says a manufacturer has small quantities of microcontrollers that need to permanently program the firmware. So we know that it's a non-volatile type of memory. It is a non-programmable, meaning the user can't program it themselves, which leaves us with mask or OTP ROM. Remember that mask programmed ROM is for mass-produced types of memory. So you're talking about like large quantities, which means OTP ROM is the answer for this first one. Oops. OTP ROM. This next question, cell phone firmware. We know that it's a large amount of code, must not be lost when the battery is died, and easy for the phone company to upgrade. So we know it's non-volatile. We know it's programmable. It can't be EPROM because you don't want to take your phone in order to do a little software update. It can't be EEPROM because that's too small, which means it must be flash. I'm just going to check to make sure that I am still recording. Yep, okay. When it's turned on, a talking teddy bear is mimicking what the child says to it after a short delay, and then forgets what it's heard. So I'm going to highlight forgets, learning a 10-second phrase or sentence and repeating back but does not retain it. So that means we have a volatile type of memory. You want to retain it for at least 10 seconds, so it's longer term than just register files. We also know it's a very short phrase, so it's not DRAM, it's going to be SRAM. And this next question, the keyword that we're concerned with is 1980s. So that automatically makes it EPROM. In this next question, we have portable. Each number is reprogrammed with a few button clicks. This is kind of a pattern where whenever we have a portable device with a small amount of data that can be reprogrammed, it's always going to be EEPROM. This next question, we have large amounts of data that's placed while it's being analyzed. The thing that they don't really, it's kind of like implicit that once you're done analyzing it, you don't really need the data anymore, right? So we're not programming anything, so it can't be non-volatile because you're only using it, you're only putting it in memory while you're using it. So it's a type of volatile memory. It's not a register file because it says specifically large amounts of data. For the same reason, we can rule out SRAM, which means DRAM is our only option. And then finally, we have here RFID tags, which contain memory. The tag's unique ID is selected and stored by the manufacturer and cannot be changed. I guess in this question, it's implicit that the RFID tags are mass-produced. Even though it says unique ID, we can rule out OTP ROM because it's being mass-produced by the manufacturer. So our answer here is mask-programmed ROM. And then finally, we have sensors, which means that it is a register file storing all our data. Okay, so moving on to our next topic, where we are going to be reviewing decimal to binary to hexadecimal conversions. Remember that when you go from an integer number to binary or hexadecimal, when you have an integer number and you're going to binary, you're going to divide by 2. When you're going from integer to hexadecimal, you're going to divide by 16. I've shown an example of going from an integer to binary over here, which is by the divide by 2 method. You can also use the addition method. This method is a little bit more intuitive to me, so that's what I end up using. And then in the case where you have a fractional number, so like a decimal meaning decimal after the decimal point number, you multiply it by 2 or by 16 if it's a hexadecimal conversion. And the method that I like to use is multiplication, but you can use the subtraction method to figure out what these numbers need to be here. We're going to walk through an example so that it's easy to understand how to convert from decimal to binary into hex. So let's do this first example where you have this decimal number of 506.625, and we're converting it first to binary, then we're converting it to hexadecimal. You can go directly from decimal to hex, if you do a base 16 conversion, but because that's just a binary, we're just going to go through each of the steps. Okay, one moment. So the first thing we're going to do is convert the integer portion. So let's do 506 convert to binary. We're going to do the division method, but so we're going to say 506. Sorry, I'm actually going to do the addition method just because it's easy for smaller numbers. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to represent our number. So let's try 2 to the 10, 10, 24. Okay, so in this case, we have 0, 2, 4, 8, 16, 32, 64, 128, 256, and 512. So with the addition method, I'm going to put a 1 for every number that I can add up to get to be 506. So I'm going to put a 0 here. Yes, I have 256. I have 128. I can add a 64. I can add a 32. I can add a 16. I can add an 8. I cannot add a 4. I can add a 2, and I'm not going to add a 0. So let's do a little check to make sure we've got it. 256 plus 128 plus 64 plus 32 plus 16 plus 8 plus 2. And that equals 506. Cool. Okay, so we've got the integer portion converted to binary. And then I'm going to walk you through how to convert this fractional portion. So first, we're going to take the fractional part of it. We're going to multiply it by 2. And we're going to get 1.25. We're going to take this decimal portion and then carry it down into our next part. So we're going to say 0.25 times 2. And then 0.5. Again, repeat the same process where we're carrying the decimal portion down until we get 1.0. You're going to repeat this multiply by 2 until you get to 1.0. Remember, I'm going to go back here. When you're doing the division method, you're going to keep going until you get a until you get like a divisor of 0. But in the case of a fractional portion, you're going to keep going until you get 1. Because at that point, once you've got 1.0, when you multiply 0.0 times 2, you're only ever going to get 0. So this just gives us a bunch of trailing zeros that we can just disregard. So the key to remember when you've done the multiplication method is you're going to read the numbers from top to bottom. So let's write our answer here. So 506.625 in binary is 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, decimal point, 1, 0, 1. I'm going to write 2 to represent that it's base 2. So let's convert binary to hexadecimal. The easiest way to do this is to just start dividing these numbers up into groups of 4. So here's one group of 4, 1, 2, 3, 4, another group of 4. You have a group of 2 here, but remember that we can always add leading zeros without impacting the value of the number. And in the case of this fractional representation, you can actually add trailing zeros in order to get 4 bits in each of those bytes. And then we're going to convert each of these numbers into hex. So 0001 is just 1, 1111 is F, 1010 is A, 1010 is again A. So I'm going to write the answer over here. So let me just write in binary again. 1, 2, 3, 4, 5, 6, 0, 0, 1, 0, 1, base 2. And then in hex, that value is 1FA dot A. And we're going to put base 16 here. Alternate representation for hexadecimal numbers, which you may have seen in your homeworks, is the 0x notation. Both of these are equivalent forms, so you can write one or the other. I'm just going to highlight these two to represent the answer. Excuse me. Okay, so I'm going to have y'all do this portion here. I'm just going to walk you through generally the steps. So this number is already in hexadecimal, so you are going to convert to binary. first. So you're going to take each of those digits and convert to binary until you get this kind of a representation. And then you're going to convert that to decimal. We're going to see how to convert a binary to decimal in part C. So let's do that over here. So first it's asking for convert to hex and then to decimal. So I'm going to write this down. 1 0 1 0 1 1 1. Wait. 1 0 1 0 1 1 1 1 0. Okay. 0 1 0 decimal point 0 1 1 0 1. Okay, so when we're converting to hex, let's do the same thing where we group by 4s. Got a group of 4 here, group of 4 here. Oops, forgot a 0. Group of 4 here, 1 2 3 4 here. We don't have enough bits in this group of 4, so we're just going to add a couple zeros to make another group of 4. We have a group of 4 here. Same situation where we're going to add trailing zeros to get another group of 4. It's important that you add trailing zeros towards the end because having just a lonesome 1 versus a 1 0 0 will change the value. So let's convert this to hex. This is 1. This is 0 1 0 1, which is 5. This is 1 1 1 0, which is 14, which I believe is E. This 0 1 1 0 is 6. 1 0 0 0 is 8. So let's write that in hex. This is 0x1 5e dot 6 8. Or alternatively, you can represent this as 15e dot 68 base 16. And then let's convert this number to decimal. You can go about it 2 ways. You can convert, you can write above the binary number, kind of like this, where it's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 5, 6. I'm actually going to erase the 0 because it's a 0. 7, 8. And then here you're going to say 2 to the minus 2, 2 to the minus 3, 2 to the 4, 2 to the minus 5 here. So that's one way you could do it. Alternatively, you can say that this is, because you already have it in hexadecimal, what you can say is this is 16 to the 0, 16 to the 1, 16 to the 2, 16 to the minus 1, 16 to the minus 2. So you can say 1 times 16 to the 2 plus 5 times 16 to the 1 plus E, which is 14, times 16 to the 0, decimal, 6 times 16 to the minus 1 plus 8 times 16 to the minus 2. And that gives us, when you put the math in your calculator or do mental math, 350.40625. And this is in base 10 because we've just converted to a decimal number. Okay, so let's moving on. Now we're at fractional representation. There's 2 ways you can represent a fraction. An integer and a fraction. The first is fixed point notation, where you have it as q n dot f. Typically, you will be given a binary number and just told that it's q n dot f notation, in which case you'll have to convert it to that form. We'll see that in an example that we're going to do below. But in this notation, n means that you have a total number of bits. F is the number of bits on the fraction. And the way you can get the number of bits on the integer is just by subtracting total number of bits minus the fractional number of bits. So let's just look at this quick example here where I have q 8.3. So in this case, where I have 8 bits in the total, I have 3 bits in the fraction. So that means I have, let me do 8 minus 3, 5 bits in the integer here. And as we can see here, we have, when we're converting 14, we're going to convert it to first figure out what the integer portion is, which is just 5 bits. And because we know that we need 3 bits of a fraction, we're just going to add zeros after that to represent it as 14.0. Our next notation is floating point notation, where it's a single position value, meaning you can represent both negative and positive numbers. You have 1 bit to represent the sign, and 8 bits to represent the exponent plus the bias. You typically bias it to be able to get like an 8-bit binary number. We're going to see it in one of our examples. So when you're going from decimal to binary, you're going to add 127. When you're going from binary to decimal, you're going to subtract 127. And the last portion of this floating point representation is the fractional bit represented with 23 bits. So as I've said, because a floating point representation can represent both negative and positive numbers, you don't need 2's complement at any given point. So let's do an example. We're going to start off with IEEE floating point representation. I'm going to write it down here. Oh, and I'm only going to be doing parts A and D because of time. It's good practice for y'all to just go ahead and do parts B, C, and E as well. So let's start with A. We've got convert 19.5625 to the IEEE format. So the first thing I'm going to do is convert 19 to an unsigned binary. So let's just do a quick division here. 19 divided by 2 is going to be 9, remainder 1, divided by 2 is 4, remainder 1, divided by 2 is 2, remainder 0, divided by 2 is 1, remainder 0, divided by 2 is 0, remainder 1. And then we're also going to convert 0.5625 to binary. First, we're going to multiply that by 2, 5625 times 2. We're going to get 1.125. We're going to take that fractional portion, so 0.125 times 2. You're going to get 0.25. 0.25 times 2. We're going to get that it's 0.5. 0.5 times 2 gives you 1.0. And this is the point where we stop. So let's put these numbers together. When you're reading from an integer to binary conversion, you go from bottom to top, which means you've got 1, 0, 0, 1, 1. And then on this case, you're going to go read from top to bottom on the stack. So we've got decimal 1, 0, 0, 1. So that's our first step. We're going to convert it to an unsigned binary number. So our second step is taking this number and putting it in whatever scientific notation is for a binary number. Right, so we're just going to do the same process of moving the decimal over. So let's do this here. Got 1, 2, 3, 4. And when I'm representing this, it's going to be 1, 0, 1, 1, 1, 0, 0, 1 times 2 to the 4th. Sorry, 1 second. Yes, so this portion here is your exponent, right? If we are comparing it to the form that we've seen before, we have 1.f times 2 to the exponent. So let's figure out what all our parts are. So this here is your f. This number here is your exponent. Remember that, oh, I think I dropped a negative sign somewhere. Oh, my bad. I started doing question B. Let's do question B and D. So in question B, the 19.5625 is a positive number, right? So the sign bit here is just going to be positive. So let's write that part. Sign bit is going to be 0. We've identified our exponent. We've identified our fractional portion. So start putting those together. So we've got exponent 4. We're going to bias it by adding 127, which gives us 131. In a binary number, this is going to be, 1 second, I seem to misplace my notes. Oh, there we go. In a binary number, this is going to be 1, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. Yep, okay. So that is the, that's the binary form of the exponent. Then we're going to write our floating point value. Remember that you're only considering this portion because this is the f portion. This is an implicit 1. You're going to ignore it. It doesn't go away. You're just going to ignore it. So we're going to write our floating point number here, 1, 1, 1, 0, 0, 1. Because we need the floating point number to be 23 bits, I'm going to add a bunch of trailing zeros in order to get it to the size that number of bits I need. So here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we got all the parts. Now we're just going to put them together. So let's start with our sign bit. And we're going to go with our binary value for the exponent. 1, 2, 3, 4, 5, 1, 2. And then we're going to write down our entire floating point number again. 0, 0, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Be very careful when you're transcribing this from your paper to the computer when doing your exam, just because it's easy to miss a 0 or 2. The best way to check is to make sure that you've got 32 digits here, 32 bits in this answer. So let's just count. 9, 10, 11, 12, 13, 14, 15, 16, 17, 21, 22, 23, 24, 25, 26, 27, 28, 30, 31, 32. Perfect. Okay, so that is our final answer for converting this into a IEEE floating point number. Okay, that's part B. Then we're going to do part D, which shows you an example of a negative number. And we're going to walk through all the steps to figure out how to convert that into decimal. So the first thing that we will have to figure out is, let's partial out all our things. So we know that the first bit is always the sign bit. The next 8 bits are going to be the exponent that has been biased. So I'm going to write biased exponent. And then we've got our answer. So of these 23 bits, this is your entire floating point. You've got several trailing zeros, right? So let's just ignore all of the zeros because they don't factor into our answer. And let's put it into the form that we need. So we've got, actually, let's first unbias the exponent. So unbias the exponent. So we're going to convert 1, 2, 3, 0, 1, 0, 0 from binary. I think I missed a 0. 1, 1, 2, 3, 4, 1, 0, 0 from binary to decimal in base 10. That means this is 132, and then we're going to unbias it. So we're going to subtract 127, which gives us 5. So let's start putting it into the form that we know. We know that we've got 1.f times 2 to the exponent, right? And then, of course, our sign bit goes out front. So in this case, it's going to be, I'm going to put that in a different color. This is our sign bit, so we know it's a negative. So let's put it down. So negative 1 point, our floating point value here is just 3 ones. 1, 1, 1 times 2 to the exponent 5. In order for us to get the complete binary number, we're going to just go back from scientific notation. So we move our decimal 1, 2, 3, 4, 5. Let's do that. We've got negative 1. So I'm going to be leaving out the negative sign just because we're trying to get the magnitude of the binary number. And then we'll add the negative back in later. So we got 1, 1, 1, and then we've got the 2 zeros. So this is our final binary number. Sorry, this is the magnitude of the binary number. And then we are going to convert to decimal. So when we convert this to decimal, we get a magnitude of 60. And then step 4, apply sign bit, which means I'm going to put a negative sign in front of the 60, and that is our final answer. So this is how you represent negative 60 in IEEE format, and vice versa. Okay. For our next topic, we have overflow and underflow and how to identify them. The first thing you need to know is how to identify the range of an unsigned integer, where n is like the number of bits that you want to represent with. We'll do an example below, but these are just kind of the formulas. So for an unsigned number, you start from 0 and you go to 2 to the n minus 1. For the range of a signed number, you have a negative sign out here. 2 to the n minus 1 going to 2 to the n minus 1 minus 1. The minus 1 is kind of outside of the exponent portion. You have to remember that for the, so I guess let me see. We'll just do an example below. And then these are the definitions for overflow and underflow. For a fixed number of bits, a binary number, it overflows when it is too large to be represented. So in a simple case, let's say we have 3 bits. So let's say example, when you have 3 bits, you can only represent numbers 0 through 7. So if I was trying to represent 8 in 3 bits, I would have an example of overflow. And then you have underflow when it is too small to be represented. So when the number is way too close to 0, you won't have enough bits to represent them. And then kind of have an example here where, it's a little bit cut off. Whereas let's say you have Q4.2. Let's do here. Q4.2. You want to represent 4.01. And the 0, 1 is way too close to 0, so you're going to have underflow. I think this might have been a typo here, so let's just scratch that out. Okay, so we're going to do an example over here. I'm just going to do the first one, and then we can go and you can try the part A yourself. So the first thing you're going to do is just make sure that you check that it's. Sorry, the first thing you do is to make sure they can be represented in the number of bits that you need. So it tells you that you have 8 bits and it's unsigned. So let's just do a quick amount of math to figure out if I can, what is the range of numbers that I can represent in 8 bits. So it's 8 to the 8 minus 1. Let me make sure I got my formula right. That's correct. Okay. So when I have 8 bits, the largest number that I can represent is 255. So 0 to 255. And then let's do a quick check. So when I add 149 and 116 in the decimal number, the sum is actually 265. 265 is greater than 255. Therefore, it's going to overflow. We can also convert 149 to binary. This is an exercise that I think y'all should do. Convert both of these to binary, sum them up, and then check if you have an extra carry. When you have an extra carry, let me write this down. When you have an extra carry, then you have overflowed, because you cannot represent the sum in 8 bits. When you check this one, check if you have an extra carry. So let's go on to part C. What is the largest unsigned number we can represent with 6 bits? So we know that n is equal to 6 in this question. The largest unsigned number we can represent is 2 to the 6 minus 1, which is going to be 63. Let me double check. Yeah. So for comparison purposes, what is a range of signed numbers that we can represent with 2 bits? So n is still equal to 6. Let's put it into our formula. Got a negative sign out here. 2 to the n minus 1, going off 2 to the n minus 1 minus 1. Parentheses. So when we have 2 to the n minus 1, that'll be 2 to the 5, which means I'm representing negative 32 all the way to 31. A quick check to make sure that you've got your range correct. Within this range, you need to have 63 numbers, or 63 digits. Okay, just a blank page, we're going to go over that. So let's go over binary arithmetic real quick. Some of the key terms that you need to remember is you have a multiplicand and a multiplier. This is just the first number that you're multiplying with the second number, and the result of that multiplication is a product. When you multiply these numbers together, typically they can be same size or different size, but when you have an n-bit multiplicand by an n-bit multiplier, your product is going to be n plus n bits in size. That is important because when you're doing signed multiplication and you apply a sign extension, you decide how long your number is going to be by figuring out what n plus n is. You're going to add more zeros to the front if it's a positive number, so like leading zeros, and then leading zeros, or you're going to add more ones if it's a negative number, so that's also just leading ones. Do not add trailing ones or zeros because that changes the magnitude of your number. And then you're going to list the first n plus n non-zero partial products. And you're always going to check your answer with decimal multiplication to make sure you're on the right track. So before we start our example, I just want to go over how to do sums and carries when you have like a non-zero number in this third digit. So we've typically only ever dealt with when you're adding 1, 2s and 1, 2, and 3 ones, which means you have, like in the case of 2, which is our most common one, your sum is 0 and your carry is 1. This carry is the one that you will store in the next column. When you're adding 3 ones together, your answer is like 0, 1, 1. So this is your sum bit and this is your carry bit. It goes into the next column. So, but when you have numbers like 4 through 7, where you have when you have like a 1 in this first column here, what you're going to do is have a sum 0. You're going to have the first carry. This is your first carry. And then you're going to have a second to carry to put a 1 in the column 2 columns over. You're going to do the same thing when you have like 5, 6, or 7. These show what your sums and carries need to be. We're going to do an example where we're going to do we're adding 4 or 5 numbers, so that'll make sense real quick. I'm going to be showing you how to do A and D. I'd like you to work through the other ones on your own. So let's do this first one here. We've got 1, 0, 1, 1, 0, 1 times 0, 1, 1, 0, 1, 0. Okay, so I'm just going to do a quick time check. Actually, I'm only going to do one of them, and then I'd like you to work through the other ones just because we're running out of time. So the first thing we're going to do is pad it with m plus n to make sure that each one is m plus n bits. So we've got, let's see, we've got 1, 2, 3, 4, 5, 6 plus 6, which means our total thing needs to be 12 bits long. Because it is a 2's complement, it's a negative number, I'm going to pad it with 1's in front. 3, 4, 5, 6, and then 1, 0, 1, 1, 0, 1. And then I'm going to pad it with zeros. 1, 2, 3, 4, 5, 6, 1, 1, 0, oops, 0, 1, 1, 0, 1, 0. Okay, so we're just going to do some multiplication. And then 1, 0, 1. I'm going to list all the non-zero partial products until this point, because after this point, everything is multiplied by 0, so it's just all going to be 0. So let me just finish writing. I've got 2 more rows. And then finally, 1, 0. I'm going to add all these up to get 0, 1, 0, 0, carry the 1, because I have 1 plus 1 plus 1, it's 1, carry the 1. 1 plus 1 is 0, carry the 1. Here I have 4 1s right here. What I'm going to do is have a 0 because the value of 4 is 1, 0, 0. So this is our sum bit. We put a 0 down. We're going to carry the next 0. That's this one over here. And then we're going to carry the 1 over onto the second column. That's this one over here. So we have 1 plus 1, 0, carry the 1. Same situation where I'm adding 4 1s. 0, carry the 0, carry the 1. In this column, 1, carry the 1. Here we have 5. Right? So we're going to say 5 in binary is 1, 0, 1. So we have a sum 1, carry the 0, carry the 1. So we've got 1 plus 1 plus 1 is 1, carry the 1. So we can continue doing the math until we get to the last digit, but we're going to stop here because we've already got 12 bits of an answer. So all of this is 12 bits. And then our final answer is going to be, write that in black, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0 in binary. So when you work through some of the other questions, you're going to do the same thing where you're going to add leading zeros or ones based on if it's a negative or a positive number, and you're going to keep multiplying until you get all the rows that you need. So if all of these were ones here, I would have another 1, 2, 3, 4, 5, 6. I would have another 7 rows of numbers that I would have to add. But remember, I only consider the first n plus n bits in my answer. Okay. Moving on to binary arithmetic. One second, I'm going to check real quick what else we have. Okay, I'm going to show binary arithmetic and floating point arithmetic. Let's do it here real quickly. So we're told that it's 2's complement multiplication, and this is the fixed point notation. So the first thing we're going to do is convert each of these numbers into our fixed point notation. So we've got 1, 1, 0, 1, 0, 1, 1, 1, multiplied by 0, 1, 0, 0, 0, 1, 0, 0. So when it says Q and dot F, we know that this portion is F. That means I have 5 decimals and 3 integers. So that's 1, 2, 3, and then 1, 2, 3. That's where our decimal goes. And then we're just going to do multiplication like we did before. I am going to skip to the answer. No, it's okay. I'll just keep multiplying. So we're going to keep multiplying until we have our first non-zero product. It's going to be a struggle to keep all these aligned, but I will do it. And then we have the next 3 rows are zeros. And then we have our final 1. So we're going to stop there. 0, 1, 0, 1, 1. We're going to add all these up carefully. 0, 0, 1, 1, 1, 0, 0, carry the 1, 0, carry the 1, 1, carry the 1, 0, carry the 1, plus 1, 0, carry the 1. Okay, even though I've done and gone ahead and done all of the numbers here, we're only going to consider the first, let me see, it's here, if I'm not mistaken. Oh no, it's hard to write that. Okay, we're only going to consider the first m plus n, where m and is the number of digits in the front. So, oh, sorry, this is Q 8.5. So we're going to consider all of these digits here. So let's put our decimal in the right spot the way we need to. So we know we have 5 fractional bits. In the first one, we have another 5 fractional bits in the second one. So I'm going to move my decimal from here 10 places over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put my decimal there. Sorry, one second. I'm just double checking that I've got this right. Okay. And then we've got 1, 1, 1, 0, dot 0, 1, 0, 0, 1, 1, 1, 0, 0. Yep. Okay. And then I'm going to write, this is our final answer. What we can do is move the decimal over to represent it in like scientific notation form, but that is just our final answer. Okay. So moving forward, this is, you can do this normalized scientific notation form once we do our next question. We're just going to do it in binary. We're going to start with addition first. So we've got 1 times 2 to the 2, and then adding it by 1.0101, 2 to the 4. So the first thing you're going to do is normalize it so that both of these exponents here are the same. And this is only a step required for addition. So we're going to say 10101, 2 to the 4. I'm going to move it over 2 decimals, equals 101.01 times 2 to the 2. And then we're going to add them. So we're going to say that's 101.01 plus 1.1011. So when I add little trailing zeros, so I can make that addition even. 114.110. And then I'm going to bring down my exponent here. This I can represent again when I normalize it as 1.101234. I move it over 2, so that's 2 to the 4. And then for the second portion where we're doing unsigned multiplication, we've got 1.101 and then 1.1010. You don't have to normalize it, but you are going to have to keep track of the exponent over there. So Just give me a second while I check my notes. Okay, so let's just figure out all our non-zero partial products. That is going to be 0, and then it's going to be 1, 0, 1, 1. Ooh, it's struggle to keep this neat. Then 1/2, 3, 5. I would recommend when you write these partial products that you go slowly because it is very easy to misalign any one of your numbers. Okay, so we've got 0, we've got 1, 0, 0, carry the 1, 1, carry the 1, 1, carry the 1, 1, carry the 1, 1, carry the 1, and 0, and put the 1 out there. And we're not going to disregard any of our carries on the side. So first we're going to place our decimal point. So we've got 4 over here and 4 over here, which means our decimal needs to be placed 2, 3, 4, 5, 6, 7, 8 positions over. So our answer is going to say 10.11110010 times 2. Where when you're doing multiplication, you add these exponents together. So 2 plus 4, which means you've got 10, 1, 2, 3, 4, 0, 0, 1, 0 times 2 to the 6th. If the question asks for you to represent this in normalized notation, you're actually going to just move the decimal over, but this is your final answer. Okay, moving forward. Our final topic is going to be adders and shifters. We're going to do an example where you're dividing two numbers, but the basic steps are the same. The first thing you're going to do is convert it to a binary number. You're going to list all of the positions of the ones. So position meaning like from 0 to whatever you have when you convert it. These positions directly correspond to the shifts. When you're writing it, you're going to left shift everything by that position. And then that your final answer would be over here once you like add the blocks together 2 out of 10. And then in the case when you're dividing, you're actually going to shift the answer right by the position of the 1 in your division, in the number that in your dividend. I think that's what it's called. But if you were multiplying instead, you would just shift it left to get the final answer. So let's just work through an example. I'm going to show what this one is. I'm going to show a diagram, and I'd like y'all to work through the other ones on your own. So we have 821 divided by 512C. So the first thing we're going to do is convert 821 to an unsigned binary number. This looks like, hang on, let me figure out what the 2 to the 9th is. 2 to the 9th is 512, so I need 2 to the 10th. So I need 10 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll put a 0 there. It's got 512, and I've got 256. Then I've got nothing for 128. Got nothing for 64, 32, 16, 16, 8, 4. Oh, I think I messed up one number? Yeah, there's 9. Hang on. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, okay, I did have an extra number somewhere. So I'm just going to go do this division way. Division 821 remainder. So 821 divided by 2 is 410. Remainder 1. 410 divided by 2. 205. Remainder 0. 205 divided by 2. 102. Remainder 1. 102 divided by 2 is 51. Remainder 0. 25. Remainder 1. 2, 12, remainder 1, divided by 2, 6, remainder 0. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder 1. Okay, this way I make sure I'm not going wrong anywhere. So we've got 1, 1, 0, 0, 1, 1, 0, 1, 0, 1. That is our binary value. Let's assign positions to all of these. 0, 1, 2, 3, 4. 5, 6, 7, 8, and 9. So remember that these positions represent our shifts. So let's go ahead and start putting these into blocks. So we've got, I'm going to write C over here. in our first block, we're going to say left shift by 9, left shift by 8, left shift by 5, shift by 4, move these over so I have to space, shift by 2. You're going to leave off the 0 because there's no point in writing left shift by 0. But it's going to come, we're going to be using that. So let's say we're going to add these in blocks of 2. And even because you're not listing left shift by 0, what you're actually going to have is have C just come down over here. So these lines represent that C is shifted by 9, C is shifted by 8, by 5, by 4, by 2, and then by 0 because there's nothing there. Then I'm going to add these blocks 2 at a time until I finally just get one block at the end. Okay. And then I'm going to have a block over here to bring this block over here, this one over here. And then before I write my final answer, remember that I have shifted my number by 512. So let's do the third part over here. Let's say convert 512 to binary. 2 to the, let me see, 2 to the 9th is actually just 512. So I still have 9 positions. 2, 3, 4, 5, 6, 7, 8, 9. So that is 512 in binary. When we write our positions, we notice that 512 is going to be shifted by 9. Because we're doing division, we are going to write this as a right shift by 9. And then our final answer here is going to be 821 divided by 512, C. So that's how you draw a diagram for adders and shifters. If I were to write an equation for this, I would just have C shifted by 9 plus C shifted by 8, C shifted by 5, C shift 4, C shift 2 plus C, and then the whole thing is going to be shifted over by 9. So that is our equation, and then this is our circuit diagram. Okay. Megan will be going over gray code, one hot and binary encoding. So that is it for part 2. Okay, I'm going to stop recording. Stop recording.